Welcome back for another lecture on earth science. We have now talked about the plate tectonics and the rock layers and um, the geologic time. Now we're going to talk about water. Water is extremely important for our earth. Obviously, water is important for life as we understand it. It's necessary for life. We can't have life as we know it without water. But it also forms the earth we live on. And so we're going to look at today at how that water forms the earth we live on. Now, just going back to 2 lectures ago, make sure that you remember something. Where are you not likely to find a volcano? So we have a convergent boundary. That's where we have two tectonic plates that are pushing toward each other. A transform boundary is where we have the two plates that are moving, sliding against each other. And then we have a divergent boundary, which is a boundary where you have two plates that are moving away from each other. And finally, a hotspot. That's like the Hawaiian Islands, where you have a place in the ocean or in the crust that is weak. So magma comes up and forms a volcano. These are shield volcanoes here from the hot spot. And all of the Hawaiian Island chain is created from one hot spot. You can't see my hands here, but you had the tectonic plates on the surface sliding over that hot spot through the mantle and punching up new islands as the crust moved over. The hot spot punched up new islands. And so the newest islands are in the Hawaiian Island chain, or in the Hawaiian Islands, but you have in that chain much older islands that have eroded away and are underwater now. So the question, where are you not likely to find a volcano? Convergent boundary, when you have two plates that come together. So here's my dense ocean plate, and here's my less dense continental plate. Then the ocean plate is going to subduct underneath, and you have grinding that melts rock, and that melted rock floats up and creates volcanoes. So convergent boundaries, volcanoes. Divergent boundaries, notice I skipped the right answer. Divergent boundaries, you have the plates pull apart, and then magma comes up between where they pulled apart. Hotspots are where you find volcanoes without having a boundary. So not that. Transform boundaries, where you are probably most likely to find no volcanoes because you're not having as violent of a grinding as you do with a convergent boundary. You're not opening up a gap as you do with a divergent boundary. Okay, the hydrologic cycle is the cycle of water. So that's what we're going to be studying here today. More than 90% of all of the Earth's water is in oceans. It's saline. So that's what you have over here. 97.2% is saline. That's not water that is useful to you and me in terms of drinking water or in terms of watering our plants. And in fact, of the water that remains, well, this is total water. So 2.14% of the Earth's water is frozen. It's in ice caps and glaciers. And so of the water that is remaining after the saline and the ice caps and glaciers, we have less than 1% of all of the Earth's water that's really available to us, water that we might think about drinking or using to water our plants. And that water is in vapor in the air, groundwater in the earth, and fresh water, like lakes and streams. So let's talk about the hydrologic cycle. The hydrologic cycle is the cycle of water moving around the earth. And it's driven by heat from the sun and by gravity. So let's start with the heat from the sun. We have an ocean here. Sunlight comes down and heats the water. As it heats the water, we've learned that The temperature will rise when you heat it, but temperature is a measurement proportional to how fast the molecules are moving. So as the sun shines on the water molecules start moving faster. And the ones that are moving fast enough can break free of the surface and evaporate and go into a gas. And so we have evaporation that is caused by the sun heating up the water. And so then we have water vapor that goes into the atmosphere. Now we have water in the air. But as that water cools, the air can't hold as much and it condenses and it falls out of the air in precipitation. So here we have water falling, here we have water falling. I am currently at 9,400 feet above sea level. How do I get water here? Well, I have a well, and what puts water in the ground so my well can pump it up? It's precipitation. If we did not have water falling from the sky, either in the form of rain or snow, or there's also variations like ice and sleet and whatever. If we didn't have that water falling, I would have no water up here. But the rain can fall on all kinds of terrain, so it can replenish the water all around the earth, not just in the low regions. Also, you'll notice there is evaporation that's coming from water that's on the ground, not in the oceans. I didn't point that out before, but it is important to point that out. It occurs. And then once the water is on the earth, it can either run off, that is, flow across the surface, or it can infiltrate, go underground, and flow underground. So gravity is what makes the water come down, and it's the heat warming up the water that makes it evaporate, and because it's high temperature, it tends to rise. Okay. I've actually talked about all the steps in the process, so I talked about everything on that slide already. Groundwater is water that is stored in the ground. We'll see later just a little more detailed definition of groundwater, so I'm not going to define it carefully here. But groundwater is affected by two important things: porosity and permeability. So porosity, think of the root word there, pore, or hole. So porosity is a measurement of how much open space there is in the rock. Now, if you think about it, you have, or in the soil, not rock. So you have soil, and the soil is made up of little grains. And these little grains are all pushed together. But there's little cavities. So if I zoom in on what I just did, you see there's little cavities like this here. And so the porosity is the measurement of the volume, there it goes, volume of open space divided by the total volume of rock. That's rock plus open space, so the total volume. And so if the porosity is low, you don't have much open space, which means you can't get much water in there. If the porosity is high, then you could store a lot of water in the soil. So porosity is telling us about how much water the soil could store if you bring water to the soil. And there's a statement here about sizes and shapes. If you have a bunch of equal size spheres, they're supposed to be equal size, the amount of open space is much bigger than it would be if you had things that were different shapes and sizes that could all fit together better. This is actually illustrated. I saw a pastor do this as a children's story once, where you have a bucket full of sand and you try to put ping pong balls in. And there's nowhere close to enough room to get the ping pong balls in because the sand packs really tightly. But then he pours the sand into a second bucket, puts the ping pong balls in the bucket, and then he pours the sand in, and then it all fits because the ping pong balls had a high porosity. There's a lot of empty space between them, and then the sand filled in all of that empty space. Whereas if you started with sand, you put the ping pong balls on, the ping pong balls couldn't fit into the porosity of the sand. So the size and shape of the particles affects the porosity. So some soils like clays, very low porosity. Others like, well, actually, I think sand is fairly high porosity. Then we have permeability. Permeability is how easily water can get through. So imagine, if you will, you have something like a pumice. Pumice is a rock that it's an igneous rock. It was molten rock that quickly froze with a whole lot of air bubbles in it. And so the pumice has lots of air holes within the rock. So its porosity is pretty high. But the way I've drawn it, those holes don't touch each other. So no water can flow through. So its permeability is low because the water can't flow through. You have to have holes that connect together for water to flow through. And so if you're going to have groundwater, you're going to have a way for water to flow in. So it has to be porous. It has to be permeable. It has to be porous to hold it, but it has to be permeable for the water to go through. And so permeability is going to have to do with how tightly packed it is and how connected the pores are. And hydraulic conductivity is a term we use to measure permeability, to tell us how easily water can flow through. Now, the more careful definition of groundwater. Groundwater is water that occurs in a saturated zone. That is, here's air, and then underneath the air we have moist soil, and then underneath that we have saturated soil. What's the difference between moist soil and saturated soil? Well, if I'm digging and I dig into moist soil, that moist soil is going to feel wet, but I don't have signs of water, the liquid water. It's just, it feels wet. Whereas if I dig down into the saturated soil, my hole is going to fill in with water because it's saturated. It's holding as much water as it can. So soil moisture is what we call the water in this moist soil. And then we have groundwater is the water in the saturated soil. And this line between the moist soil and the saturated soil, we call that the water table. So above the water table, you have moisture in the soil, but you don't have saturation. You're not going to see water per se. Whereas below the water table, you dig into it, it's just going to fill with water. So when you are digging a well, you don't want to dig that well just down into moist soil. You want to dig that well down into the water table or below the water table so you have groundwater so that you pump water out and the groundwater fills it back in. Now, how quickly it fills in depends on the permeability of the soil. If the soil is highly permeable, it will fill in fairly quickly. If it's not so permeable, it will be a slower process of filling in. Of course, if you dig deeper into the water table, then you have more area for the water to come in and it will refill faster. So here's an example showing how the water table varies. So we have a house up here on a ridge, and they have their well, and their well is dug down so that they're below the water table. So the water table is this dashed line. You see a problem here? It has the water table normal, and then it has the water table during drought. What's going to happen to that well if you get into drought? If the water table drops down below here, you have a dry well. These people are not going to have water from their well because they didn't dig deep enough. They need to dig down so they are well below the drought level for the water table to be safe in case of a drought. Now, the water table varies with position. So here the water table is coming down as the exterior comes down, but here the water table is above ground level. If the water table is above ground level, then you're going to have water on top of the ground. And so in this case, it labeled it as a stream, water flowing through. It could just be a lake. A lake is a place where the water table is above the ground level. And so you have water that sits on top of the ground, a lake. Obviously, oceans have that similar arrangement that the water table is above the ground level. Now, as a child, I grew up in Monterey Bay Academy. We went to the beach all the time. And one of the things I loved to do was dig down into the sand. And you dig down to the sand, and you dig down deep enough. So here's the sand. You dig down deep enough, and it will have a little pool. I didn't have to put water in that pool. It just came through the sand. I didn't understand the reasoning of what was going on, but now we can explain it. The water table was here. And so, when you're at the beach, you're not that far from the ocean. And so the water table is pretty much at the level you are. And so you don't have to dig down very much, and you get these, natural little pools that occur. Now we have the term aquifer. An aquifer is a reservoir of groundwater. So it's underwater. Now, one of the things I want to make sure is really clear. If I have an aquifer, that doesn't mean that I have a pool that I could swim in under here. This aquifer is porous, permeable soil. So we have lots of soil in here, but all of the pores are filled with water. So you can't swim in an aquifer, right? It's a reservoir, but you can't swim in it. It's soil that is saturated. They're a vital source of fresh water. And like I said, high porosity and high permeability. High porosity, lots of storage space. High permeability, water can go through it easily. So, do you know anything about aquifers? Well, you should. We live on top, we go to school on top of the Ogallala Aquifer, also known as the High Plains Aquifer. So this picture shows the Ogallala Aquifer, and you can see, now I say we live, actually, we might not. I think Lancaster County's here, so I think we might not be on top of the aquifer, but most of Nebraska has the aquifer underneath it. And this aquifer is enormous, coming all the way down into Texas, and it's water stored in the soil. And if you look here, you can see that in some regions, so Ogallala is about here. In some regions, so close there north to Ogallala, you have between 1,000 and 1,200 feet thick. That is the depth from the top to the bottom of the aquifer is over 1,000 feet. That's a very big aquifer, of course. And if you take the horizontal aspect, it's an enormous aquifer. It's very important. This, and I know I'm going to get political here, this is why I personally stand in opposition to the Keystone XL pipeline. They want to put a pipeline that goes through or across this aquifer. But that is a vital source of water, of fresh water. And if you were to have a leak in that pipeline, then you would have potential contamination of this entire aquifer. And, I remember when we were opposing, I actually went and participated in a protest against the Keystone XL pipeline. And the pro-pipeline people were saying, everything is computer controlled. If it has a leak, it will be immediately detected, and the oil flow will stop and so on. And yet we see time and again that there will be leaks in these pipelines, and it will leak for days before anyone even realizes that they've leaked thousands of barrels of oil. So that's why I stand in opposition, because I want to protect that aquifer. You probably have heard about artesian springs. And just to make sure we know exactly what's going on, here's an example showing we have a mountain area here. So this is up in a mountain, and it rains. And then the water is going to recharge an aquifer. That is, it's filling the aquifer. And so the water level in this aquifer is right here. Now, as water flows through the aquifer, there's a certain resistance to the water flowing through. And so that resistance means that your pressure is not as high. Remember, we learned before in our physics section, the pressure difference is density times G times the height difference. And so we can calculate a pressure difference from, let's say, here to here based on that height difference. I know that's not a horizontal line. I tried. That's more horizontal. So based on the height difference here, we could calculate what the pressure should be of water coming out of the ground. But the pressure actually drops because of the losses we go through here. So the water table is dropping, and we really only have the pressure difference between where that water table is and where the hole in the ground is. So it's a very small pressure here comparatively. But what makes this an artesian well is that we have a hole going through a low permeability rock that allows water from the aquifer to come up, and the water table is above ground level. So that means the pressure down here is going to push the water up and out of the ground. So artesian well, you just have natural water coming up out of the ground. It's a wonderful thing if you're, out exploring and you want to homestead, and here you find an artesian well on this property. You build your house there. You don't have to dig a well. You have natural water coming out of the ground. It's because you had pressurized water down below that's pushing up through a hole in the low permeability rock. Now, if you look up here, you have a hole in the low permeability rock, but the water table is below the elevation of the ground. So in that case, it's a dry artesian well. It's not flowing. You have the artesian well because you have the hole there, but it's not flowing. What's the difference in the spring and the well? Their illustration is trying to show you that the spring, you have the height of the water table is above ground level on both sides, whereas the well, it's not above ground level on one side, it's only above on the other side. So that's what artesian wells are all about, or artesian springs. It's when your water table is above ground level and you have a hole in the non-permeable rock that allows you to then have water come up. Now, a perched water table is an interesting thing. Let's suppose you put your house here and you have a well. And you go down and, hey, you hit water. That's great, right? But this is a perched water table. You have a low permeability layer, and then you have water sitting on top. That's why they call it perched. So what would happen if you put your well into that perched water table? You pump it out, and what do you have? No water table anymore. So that would be a bad situation if you drilled down and you stopped here. You would need to keep going down into the main water table so that you have a replenishable water table. This spring here is water coming off. So it's basically an artesian spring from that perched water table. This stream is where the water table is above ground level. Now, you do not have to know this Darcy's law, but we talked about the water pressure dropping because of going through the rock. And so the groundwater flow rate is calculated by taking the hydraulic conductivity, that is how permeable the rock is, times the cross-sectional area, the area that's going through, and then finally the hydraulic gradient. The hydraulic gradient is the difference in elevation between the starting and ending points. Now, water table is something that is a slightly different idea, but it's the same thing. You have a waterhead that is the difference between elevations of, here's where the water table is here. You couldn't see that. Here's the water table here. Here's the water table here. The hydraulic head is the difference in elevation between those water tables. And that's telling you how much pressure potentially you could produce. Now, groundwater causes a whole lot of crazy things. This here we call a sinkhole. So that's what this. And we'll learn about sinkholes in this little section, but you can see here that this here is the stripe that used to continue on here. And it's very clear that the ground underneath the road eroded out. Why would it erode out? Most likely, you had a water pipe under here that sprung a leak, and that water then washed soil away, leaving an empty cavern, and then the ground fell in that cavern. Subsidence is, well, I'm from California. This is a picture taken in the San Joaquin Valley. It's a very fertile valley where a huge amount of the produce for the world is produced. But what are they doing? They're pumping groundwater out to irrigate those crops. You can see in this picture the crops there growing in the background, right? It's a very fertile ground. But as they pump that water out, you have the soil particles that were partially being held up by water. You take out the water and they collapse together. Well, they collapse together, that's going to decrease the porosity and it's going to decrease the permeability. So if you bring water in, the water won't fill it back up as much. So the ground level has dropped. You can see this is where the Earth was in 1925. In 1955, the ground level had dropped to there. By 1977, that's when this picture was taken. Here's the ground level. And so you have this enormous drop. It's a total of, by 1970, it had dropped as much as 28 feet because of them pumping the water out of the ground. That's scary to me. It really is. We need the water for agriculture, but maybe pumping out of the ground there wasn't the good idea. So that's what we call subsidence. The land sinking down when you pull the water out. Now, underground caverns and caves. A cavern's a really big cave. Water going underground, if it's flowing, it can eat away rock, especially limestone. Why limestone? Limestone, which is a calcium carbonate derivative, is water soluble. That is, it formed from precipitate out of water. And if you have water flowing through, you can dissolve it back. And so if you have limestone, you have water flow through, such as Ruby Falls in Tennessee, a good example, then it just eats away that limestone. And so if you have acid rain, it will acidic water, it will much more readily etch it away and dissolve it. And so you get caverns. Now, this here is just a picture showing what happens when water flows through a limestone rock. So here you have initial case, water's flowing here. It's seeping through because you have some permeability and porosity. And as it goes through here, it's washing away stone. As it washes away stone, then it kind of collapses. And you can see here lots of collapsing and leaving behind caverns. So these black things are caverns, places where you have gaps. Sinkholes, well, I already talked about them because I had the picture. They're funnel-shaped cavities in the ground that are open to the sky. Open to the sky because, well, it fell down. One of the famous ones occurred in Kentucky, maybe 10 years ago, in a Corvette museum. All of a sudden, boom, they had a couple cars that fell down because of a sinkhole. Don't worry about the car screeches. I'm not going to talk about this. So now we're changing. We were talking about sinkholes and caverns. Now we're going to talk about surface water and drainage systems. So surface water, that's things that is on the surface of the ground. So water on the surface, a stream is on the surface, a lake is on the surface, a river is on the surface. Those are things that we call surface water. And surface water is just a minute proportion of the available water to us. Remember, less than 1% of all water on Earth is available to us. And of that water, almost all of it is underground. So the surface water, what we see, is a really small portion of the Earth's water, and that's not counting oceans. Infiltration is the process of water going from surface water into groundwater. And that would depend upon how much rain you have, how long it is. When it first starts to rain, the water will go into the ground. If it rains slowly for a long period of time, you'll have almost all that water just go into the ground. If it rains rapidly, well, then you can have a lot of it that stays on top because too much water couldn't go in that quickly. Um, Obviously, it depends on soil type. Some soils will absorb more water, others less. And the slope, if the slope is like this, you're going to have a lot of water flowing down. If the slope is like this, you're going to have a lot of water infiltrating. And the vegetation will make a difference in how porous it is. Running water shapes the earth because it carves out landscapes and it deposits. It does both. And so let's look at how it carves. Well, first, we're going to have this picture twice. Once talking about how it carves and just one talking about stream flow. So if I have water flowing in a stream, the water's coming like this and the edge makes it turn. And what you're going to have is maximum speed out here in the part where it was turning. So this is fast. On this side, it's going to be slow moving. And so the zigzag shown is showing where the bulk of your water is going. And when you have that fast water, it's going to dig out. And so it's deeper there where it's fast and it's eroding in. If it's, a straight shot, then it's going to be fast in the center and it's more uniform. So these are corresponding to locations. So maximum speed will be on the outside of a curve, minimum speed on the inside of a curve. Maybe I have these out of order because I told them I'm going to come back to that slide. Drainage basins, when I was a kid, I didn't know what the Continental Divide meant. I thought the Continental Divide must be something like this, dividing the continent into its east and its west. Well, I was just straight wrong. Just wrong. That's not what the divide is at all. Hopefully, if I do enough undos, there we go. So the Continental Divide is actually this red line. And what it has to do with is drainage of water. If it rains in the mountains, where's the water go? Well, it depends on which side of the Continental Divide you're on. If you're on this side of the Continental Divide, that water ends up going to the Gulf. Well, let me not use, let's just say it goes to the Atlantic Ocean. Atlantic Ocean. So any water that's on the east side of the Continental Divide will eventually flow into the Atlantic Ocean. Whereas if it is on the west side, then it will flow into the Pacific Ocean. So the Continental Divide is dividing where water flows. So you notice my two starting points here were virtually right next to each other. And so the Continental Divide, if you go to that spot where I zoom in, I just erased a lot probably. If you go to this spot right here, and it rains, you'd see some water go this way and go to the Pacific, and some water go this way and go to the Atlantic. Now, where I am today, I am in Colorado, and I am somewhere really close to here. And so water that rains here, I'm on this side, it's all going to the Atlantic Ocean. But if I go to Monarch Crest, it's right here on the top, and we have the Continental Divide. And so the Colorado River goes west from basically my location. The Arkansas goes east from my location, and they carry the waters to different oceans. Surface water, as I said earlier, boy, I don't know, maybe this is a repeat slide. It causes erosion and deposition. So let's first talk about that process. We have streams will flow in a laminar flow. Laminar means in layers. So it's a smooth flow. A smooth flow is slow and gentle and it's likely to drop off material. A turbulent flow, that there you have the water doing crazy loopy things, and it is going to do a lot more to pick up material. So fast flows tend to be turbulent. It depends on the geometry of the stream, how fast is turbulent. So you have water that will be smooth, and then you come to the rapids. The rapids are places where you have rocks and stuff that makes it so it turns into a turbulent flow. So laminar flows versus turbulent flows are important for understanding how a stream transports water. Laminar flows can lift and carry only very small particles. So laminar flows usually aren't carrying much. It's usually going to be cleaner water, so it's better for swimming. Turbulent flows can carry and move large particles. And so they're going to carry lots of stuff. You're going to have murky water with lots of particles in it. You take a mouthful of that, and it's going to be all gritty because of the sanding. I'm going to come back to a picture, that deals with the deposition. But first, the picking up, weathering. Weathering is breaking rock apart. And you can break apart rock through chemical weathering. That is something like if you have an acid, it will dissolve a limestone rock. You can also have hydraulic action. Water flowing by will grind. When I was a kid and I saw these things, I always thought that those were the Indians had used to grind out their corn. And I thought they were made by the Indians. Now, I think it's true the Indians used those, at least where I grew up, to grind out corn, but they were naturally occurring because there were places where you had some rock or sand. As water flows, that rock or sand moves around in here and grinds the rock out, making a bigger and bigger hole. And so abrasion is that process of the water causing material to grind it out. So those are ways that water will erode rock. Now, of course, if it was already sand or soil, the water can pick it up much more easily. So in stream erosion, loosely consolidated particles, that is, things that aren't tightly packed, are lifted by abrasion and dissolution, and then they're carried. And stronger currents will carry things more effectively, carry at larger distances, and have a lot more in them. And so you tend to develop stream channels because of erosion. Now notice the stream channel, it's shaped like a V. You have water that came down here and it's eroded. And as it erodes, it just makes it a sharper and sharper V. This here, I'm pretty sure, is in Yellowstone, the falls there in Yellowstone. It's a pretty falls. And so you have a waterfall here. Why is there a waterfall here? Because you have a rock here that's harder, that doesn't erode as easily. And so the water came over that, and then something that was easily eroded down and created this much lower valley. So stream channels cut V-shaped canyons. And now we come back to the picture about erosion. So it's the same picture as before, but before we were just talking about the speed. Now we're talking about what happens with the speed. If you have the fast moving water, it erodes. So you have erosion here because of fast water. Where it's slow, you have deposition because slow water can't hold as much. And so you tend to have a sandbar here because you deposited material on that inside part of the corner and you erode outward. And so what's going to happen over time is this stream is going to get more and more extreme as it erodes outward. And you create these sandbars where it's depositing. And so we have stream valleys. If we have a fairly flat stream, the stream will bring down material, it'll erode and deposit. And if you have a curve, which you always have some curves, the curve is going to move out. And so the curves move out, and so your stream will erode back and forth across a relatively flat valley, creating a floodplain where the stream has flattened everything out. Now, this is great for farming. If you're farming, you love this because what you have is a soil that is deposition from the stream filled with all kinds of good things for growing and a nice level area for farming. But as we saw last year, it can really cause problems. So here's a picture showing the progression of a floodplain. So you started with a waterfall and then a valley where it meanders back and forth. But that meandering back and forth continued, and so now we don't have the waterfall anymore. It's eroded away, and we have a valley that is bigger. And over time, that valley gets bigger and bigger and bigger and bigger and bigger. And let's notice some other features. See this right here? Well, if you go to the previous picture, you had, and it's hard to match up exactly, but I think that's this here. What happened was it got so extreme that when you had a flood event, the flood event punched through and cut that off. So this here we call an oxbow lake. You ever seen an oxbow lake? Well, if you have ever flown into Epley Airport in Omaha, then absolutely you have. Because in Omaha, and I can't believe I didn't, well, I have a picture coming up that's something like this, but if you, well, let's just go to my web browser and just look up in the maps. Epley Airfield, I missed. Excellent. Here, Epley Airfield. Bring up the map, maybe. Of course, I clicked again too late. So if we look at the map here of Epley Airfield, as it slowly responds, it's loading, as you can see. Come on. I just want to shrink this a little bit. We can now see Carter Lake. All right, finally it responds to me. So let's look at the boundary between Iowa and Nebraska here. Zoom out a little more. So the boundary between Iowa and Nebraska is coming down here in the middle of the Missouri River. And it comes up like this, goes up Abbott Drive, which is the drive you come into the airport. Comes down and rejoins the Missouri River. Why does it do that? It does that because the river used to go like this. But when you had a flood, the flood caused it to flow rapidly. As it flowed rapidly, it cut across here, creating a new path for the river and leaving off this region that used to be part of the river. So this up here is no longer part of the river. But when the border was drawn, it was part of the river. And so we now have Carter Lake out here that's an oxbow lake. And all of this inside of here is Iowa. And out here is Nebraska. So that's an oxbow lake. And if you follow the border north and south, you'll find more oxbow lakes like that, places where the boundary, which used to be right in the center of the Missouri River, is no longer at the center of the Missouri River. So there's a good example of an oxbow lake. So I find this very interesting. Now, what happens when water gets to the end of a stream? It hits the ocean. When it hits the ocean, it's going to slow down. But slow water deposits, just like we had on the inside curves of a stream, it deposits on the outside erodes. And so when you have water hitting the ocean, you have all of a sudden a whole bunch of deposition, which tends to form a fan-shaped region of deposition. And so we call it a delta because a capital delta looks like that. And so deltas are where you have water flowing into standing water, such as where the Mississippi River reaches the ocean. Now, in this picture, what geologic feature are you seeing? Are you seeing a delta? Do you see water flowing into an ocean? No. Do you see turbulent flow? I can't see turbulent flow. Rapids go with turbulent flow. What we have is a floodplain. We have a flat region here that has been carved out by this river. Now, a year ago, we had some significant flooding here near Lincoln. So here are pictures I took from March of 2000. I didn't take. I got these from a website from NASA. Got the link there. March 20, 2018 and March 16, 2019. And you see a big difference. You have floodplain. Here's floodplain that just had the river flowing through in its path. But that was in 2018. Last year in 2019, you see that floodplain was pretty much flooded. And so Offutt Air Force Base was flooded. Part of its runways were underwater. And you had up here completely flooded. Why? Well, you had more water flowing down the stream, and that water then expanded to fill more of the floodplain. It's not good to build your house in that floodplain, is it? Normally, it's great. I mean, you're farming there. It's great farmland, and you build your structures in there, but you have to know that those are suspect. They're probably not going to survive. Look at this here. That there, most of their stuff is probably underwater because they built in a floodplain. So that is the entire picture. So you can see the effects of water. Now here, what are we seeing? Is it a floodplain? I always start with, is that a floodplain? Well, I mean, maybe there's a floodplain here. It's hard to tell. Definitely not that. So maybe a floodplain, but it does have a very significant feature. This here, okay, so it's really a fan, but we call it a delta. That's a delta. That's water going into the ocean. And because it's going into the ocean, it really slows down. Because it really slows down, it's deposited all kinds of sediment here. Now, for our final trick, we'll talk about glaciers. Glaciers, you have two kinds, alpine glaciers and continental glaciers. Alpine or high mountains, continental, that's what I would have here. But glaciers are places where you have more snow accumulation than you have evaporation each year. And so you grow a bigger and bigger sheet of ice. And the pressure of, if you have a slope, then the pressure difference will actually make the glacier flow. And so it has plastic deformation. That means it deforms in a manner that makes it permanently deform. And so this line here showing at, let's say today, it's a straight down line. And if I wait a week, this here is where that material is a week later. So the top part flowed a lot more than the bottom part is what this is indicating. You have bedrock down here. What do you suppose happens when you have ice sliding over bedrock? It grinds up ice. Well, that's no big deal. We just form water. And it grinds up bedrock. And so it's going to drag and grind underneath it. And so, well, we don't have that yet in our picture, but we have what we call moraine, the ground up rock that gets pulled down by that. Flowing glaciers have accumulation zones, places where you get more snowing than evaporation, and it grows. And then it's flowing. You have sublimation that's going from solid ice into vapor without becoming liquid. We call this ablation anywhere where it's losing. And then you have here where it's melting and calving. Calving is breaking off. And so notice here, the end of this glacier is retreating. Most glaciers today are retreating. Why? Well, we believe because temperatures are getting higher. And with temperatures getting higher, well, it's natural for the glacier to retreat because you have more sublimation, more melting. So here is on the right, very near and dear to my heart, this is Yosemite Valley. And so you have features like way back here in the background. Let's see if I can zoom in. You have the ever famous Half Dome. You have here the captain, El Capitan, the largest monolith of granite, I think, on Earth, at least in North America. And it's just a beautiful place. Notice it's kind of a U-shaped valley. That's because it's a glacier carved valley. The Yosemite Valley is U-shaped, and it's the typical shape for glacier formed valleys where you ground it out. Now this here, this is showing a flowing glacier. You have ice that is flowing down like this, flowing in like this, flowing like this, flowing like this. What's all that black stuff? That black stuff is called moraine. It's ground up rock. And this is side moraine. That is, it's moraine, ground up rock from the sides of the glacier. So if I follow some of that, here's the side of this glacier, and then here it merged. Here's the side of this one, and it merged. And so this here is the moraine from where the two merged, and now it's in the center of the glacier of the flow because it merged. And so likewise, you have from the edge of this one going here, from the edge of this one going here, giving us this moraine. So that's moraine. It's ground up rock that's flowing along with the glacier. When I first looked at a picture like this, being naive, not knowing anything, I thought, wow, that's a silly place to build a road. Because that's what it looked like to me. It looked like somebody had built a highway on top of the glacier. That's not what it is. It's just ground up rock, otherwise known as moraine. When a great glacier retreats, at its farthest point, you have what we call the terminal moraine. So there's how you spell moraine. The terminal moraine is the rock that was pushed along as it slid down. And then when it starts backing up, that rock stays there. So if you look, that buildup at the end is the terminal, but you have moraine all the way back. And then you have other features. Eskers are these little streams that were flowing under the glacier. And you have drumlins. Drumlins are places where a rock is kind of gouged out, a teardrop shape. You have kettle lakes. These are all features that we see from glaciers. Glaciers leave lots of things like these drumlins and eskers, and in the end, lots of lakes. So, Minnesota, the land of, 10,000 lakes. Why does it have 10,000 lakes? Because it used to be covered by a glacier. The glacier retreated, and it left all of these features that then form all of those lakes that they have in Minnesota. A last segment I have here, I forgot I even had this, is the work of air. Sand dunes are created, and this is also the way that you create the washboard roads, sadly, that we have out here. If you have wind blowing, the blowing wind will pick up sand. But then if you get to the end of a bump, it slows down and it drops the sand out. And so it keeps building on this side. So you take sand off of this, you build it here, and you build a bigger and bigger sand dune. So the wind shadow, the side where the wind was going toward, when it gets past the sand dune, it drops it off, and that's called the leeward slope. That's how I learned to talk about when I was taking sailing on back in grade school. The windward side is the side the wind's coming from. So it builds up a flat ramp on the windward side and then drops and builds higher on the leeward side. This is where we will end today's lecture. There are many erosive agents that sculpt the Earth's surface. Overall, the most erosive agent that does the most work is, what do you suppose? We just talked about wind. It does erosive work. Groundwater. Groundwater does erosive work. That's how you have your caverns and sinkholes. Glaciers, they do a lot of work slowly. But running water is the biggest erosive agent. It's doing the most changing of what we see. All right. Have a great day.